Yun Hong Sang is currently an associate professor in the Department of Applied Physics in the Polytechnic University. Today, our first talk is given by Dr. ZHU. And Dr. ZHU is currently an associate professor in the Department of Applied Physics, the Hong Kong Polytechnic University. Dr. Zhu has dedicated to developing cutting-edge microscope and spectroscopy techniques and their application on emerging materials. Applying this technique, his team has made enormous breakthroughs, including the first discovery of novel 2D anti-ferroelectricity and ferroelasticity in indium selenide compounds. Today, he will give us a very interesting talk regarding the application of TEM technology on energy material. Let's welcome Dr. Zhu Ye. It's your turn now, Dr. Zhu Ye.
Yeah, so can you see my slides?
Yeah, excellent, see.
Okay, thanks for the introduction. Good afternoon, everyone. I'm Zhu Ye from the Applied Physics Department at PolyU. So first, I would like to thank the organizer for inviting me to this wonderful event. I have learned a lot in the fields of battery and the catalysis. So my group is specialized in TEM technique and its application on material characterization. So different from most of the previous talks, which focus on the particular energy problem, my talk will focus on the TEM technology and how it may contribute to the energy material research. So that includes to use this scanning TEM or STEM to image the atomic structure and the lattice distortion in the energy materials, and also the in situ liquid TEM to directly capture the reaction dynamics for this OER catalysis. So as a microscopist, we are interested in the structure, and the importance of structure characterization is well said by the Nobel laureate Francis Crick. If you want to understand function, study structure. Francis Crick used X-ray diffraction to discover the double helix structure of DNA. Actually, till today, over 90% of material structures were solved by X-ray diffraction. So why do we want to use TEM to deal with the structure? That's because for the diffraction-based method, it always requires high-quality crystals, and for materials with poor crystallinity or the large unit cells, such as those containing large molecules and supercells, they will give rather complicated diffraction signal, which can be challenging for structure analysis. But for these materials, TEM offers a powerful alternative to directly image the structure in real space with very high resolution. And that is reflected by the recent success of the cryo-EM, which has already been used to solve the hundreds of structures of biomolecules that are difficult to crystallize. So it won the Nobel Prize in Chemistry in 2017. And this diagram summarizes the progress of resolution improvement for the microscopes. When the optical microscope reached the diffraction limit, the electron microscope was invented, and its resolution quickly approaches the atomic level. So that is due to the, there's some problem with the display here. So that is due to the short de Broglie wavelengths of the electrons. But the short wavelengths applied for both electrons and X-ray. And due to the charged nature of the electrons, we can use the electromagnetic lens to effectively focus the electrons to form the high resolution image, which cannot be easily achieved for the X-ray. And with the advent of the aberration-corrected, today's TEM can routinely reach sub-angstrom resolution, which makes it unique in probing the local structure of the materials. So modern TEM offers different imaging modes, and STEM is one of the most popular modes. In STEM, we focus the electron into a small probe and scan it over the sample surface, just like the SEM. But different from the SEM, in STEM, the electrons can be focused down to the sub-angstrom level. And we are collecting the transmitted electrons, which carry the information about the bulk structure. So for the heavy atoms inside the sample, it will scatter electrons to the high angle, which can be collected by this annular dark field detector. So the from the ADF STEM image will mostly show the heavy elements, such as this A and B cations in this perovskite material. And for the light elements, they will scatter electrons to the low angle that can be collected by this bright field detector. So in the bright field STEM image, it will be more sensitive to the light elements, such as this oxygen octahedral. So by controlling this collection angle, we can tune the relative contrast between the light and the heavy elements so that we can focus on the element that we are interested in. So this has been very useful when I work on this lithium solid electrolyte material, this lithium neodymium titanate, or LNT. So LNT is not a particularly good solid electrolyte, but it exhibits this interesting nanodomain structure, which is periodic in 2D. And this nanodomain pattern is lithium dependent. So here we are using the electron energy loss spectroscopy EELS to detect the presence of lithium. We can see when the lithium is all gone, the nanodomain pattern also disappears. And when lithium comes back, the nanodomain pattern will recover. So this indicates these nanodomains are relevant to the lithium transport in this solid electrolyte material. So to understand the nature of these nanodomains, we performed the high resolution STEM imaging. So normally people will just look at the ADF STEM image for the heavy elements. But here in this image, it only shows the regular perovskite lattice without the nanodomain contrast. So only when we look at the bright field STEM image, we can see the interesting lattice distortion. So this is a magnified image from this squared region. Here, the bright dots correspond to the oxygen columns, which form this octahedral. And we can see the neighboring octahedral are tilted towards the opposite direction. And this is a simulated image for comparison. This octahedral tilting is a common lattice distortion in the perovskite material. But what's interesting about this LNT is that the octahedral tilting is not uniform. So in the neighboring region, inside this black square, we can see the octahedral are not tilted at all. So it is this 2D modulated octahedral tilting give rise to this nanodomain pattern. And with the sub-angstrom resolution in our image, we can precisely measure the position of each oxygen columns as indicated by these green dots. And if we connect these dots to form the octahedral network, we can see the octahedral are tilted in this region. And we can use different color to indicate different tilting direction and magnitude as indicated by the red and the cyan color here. So after color coded this map, we can clearly see a nanodomain pattern, which is consistent with the low mag observation that we've seen before. So not only this confirms the octahedral tilt is the modulated octahedral tilt is the reason to form this nanodomain pattern, but it also demonstrates a powerful imaging mode to quantitatively measure the octahedral tilt angle. So we have mentioned that this nanodomain pattern is lithium dependent. So to further explore this lithium dependence, we performed this octahedral tilt mapping in the LNT with different lithium content. Previously, we have been looking at this high lithium content LNT. And by reducing the lithium content, we can see both the nanodomain size and the octahedral tilt angle are greatly reduced. So as mentioned before, when the lithium is reduced to 0, the nanodomain pattern will disappear completely. So this demonstrates the coupling between the lithium content and the octahedral tilt, which is summarized in this table. So basically, the higher the lithium content, the higher the measured octahedral tilt angle, and also the larger these nanodomains will be. So why is there such a coupling? For perovskite materials, the structure stability is indicated by this tolerance factor as defined by this formula. Here, this parameter R are the ionic radiance for the A and B cations and the oxygen anions. If the tolerance factor approaches 1, then we will have the stable perovskite structure like this. But for the small A cations, such as the lithium, it will give a very small tolerance factor. And to accommodate these small A cations, the oxygen octahedral will tend to tilt so that these two oxygen can be better bonded to this small lithium atom. So this means the smaller the A cation, the larger the octahedral tilt angle, and also the smaller the tolerance factor. So this coupling has been experimentally confirmed in the perovskite material. And based on this consideration, in the LNT material, the higher the lithium content, the smaller the tolerance factor will be. So the higher the octahedral tilt we will see. So that is consistent with our observation. So this is rather an old example to demonstrate how the sub-angstrom resolution imaging can help us to understand the energy materials. And as one of the most recent example, we apply a similar technique on this copper catalyst with excellent performance for the CO2 reduction. So this work is led by Professor Lau in our department, who have talked about this yesterday. So basically, in TEM, we observed lots of planar defects inside the copper catalyst. More importantly, these planar defects will give rise to the step phases at the surface, which tends to show low coordination number and also the tensile strain. So with the sub-angstrom resolution in our image, we can reliably measure this tensile strain, which is about 1%. And this is consistent with the synchrotron X-ray analysis. Both the tensile strain and the reduced coordination should contribute to the very good performance for the CO2 reduction. So besides the high resolution imaging, modern TEM can also acquire spectroscopy such as EELS. In the first example, we already used the EELS to detect the presence of lithium in the LNT material. And in STEM, during the scanning, we can acquire a EELS spectrum at every scan position to achieve this spectroscopic mapping. So here we can see due to the smaller interaction volume from this sub-angstrom probe, this EELS mapping can achieve the atomic resolution as demonstrated here. We can clearly see the individual barium atoms embedded in the strontium titanate lattice to form this artificial superlattice. So next, I will show you how this atomic resolution EELS mapping can help to understand the structure and the performance of the doped catalysts. So this is in collaboration with Professor Crick at Australia National University. So his group developed this system using manganese oxide to oxidize methane to form CO and hydrogen. And the manganese oxide will be reduced to the carbide. Then the manganese carbide can be further used to react with CO2 to generate manganese oxide and CO. So with these high temperature reactions, this system can continuously convert this greenhouse gas into CO and hydrogen. More interestingly, by adding 3% cerium dopant, the production rate of CO and hydrogen can be greatly enhanced. So next, we try to understand how this performance enhancement comes from. So we first perform the high resolution imaging to detect the presence of the cerium dopants. As showing this ADF STEM image, the cerium dopant can exist in terms of individual dopants or the nanoclusters embedded in the manganese oxide lattice. They can also segregate at the 101 phases as monolayer cerium oxide. So this shows this ADF STEM image seems to be effective in detecting all the dopants. However, only after we compare with spectroscopic mapping, we realize that not all the dopants are detected by this high resolution image. So as shown in this area, it appears there's no dopant in this region, but when we apply this atomic resolution EELS mapping, we can clearly identify this cerium dopant located at this position. So this indicates EELS mapping offers much higher sensitivity compared to the high resolution STEM imaging. So this different sensitivity can be understood from their different contrast mechanism. For the high resolution imaging, the different contrast comes from the different electron scattering between cerium and manganese. But if there's only one cerium dopant embedded in this manganese column compared to a pure manganese column, the difference will be small, which will give a weak contrast below the noise level. But for the EELS mapping, even though a single dopant cerium will still give a weak signal, but compared to the pure manganese column without any cerium, the contrast will still be big enough. So it will give higher sensitivity for the EELS map to detect the dopants. On the other hand, even though we can reliably detect the position of the dopants, we still don't know whether there are 1 or 2 or 3 cerium dopant at this position. So to address this issue, we have performed the dedicated EELS simulation, which shows that the intensity of the EELS signal should be linearly proportional to the number of dopants along the column. So this means by quantitatively measure the EELS intensity from this map, we can do the dopant counting column by column, which will give us more complete information about the dopant distribution. And with the fine structure of EELS, we can also derive the oxidation states of the cerium and the manganese. So here the pink spectrum is from the cerium nanocluster embedded in the manganese oxide, which is consistent with the cerium 4+ species. So this indicates the nanoclusters should be cerium 02. And the cyan spectrum are taken from the surface cerium, which shows a reduced valence compared to the cerium 4+. And during the STEM observation, we often see the hopping of the cerium inside the manganese oxide lattice. So this indicates high mobility of the cerium dopant inside the lattice, which has also been confirmed by the DFT calculation. So this high mobility of cerium suggests that there could be an easy conversion between different configuration of the dopants. So for this first two reactions, with this reduced methane atmosphere, the surface cerium with lower valence should be preferred, so that the embedded cerium may tend to migrate towards the surface to have the reduced valence. And this migration will provide an easy route to release oxygen inside the manganese oxide, which will lead to a more complete conversion to the manganese carbide. And for the last reaction, the opposite process will occur in this oxidative atmosphere. So the surface cerium will tend to migrate into the lattice, which will bring more oxygen for more complete oxidation. And without the cerium dopant, all these reactions will become less complete, which give rise to a lower production rate. So besides the high resolution imaging and the spectroscopic mapping, modern TEM also offers this in situ capability that is enabled by various in situ holders. So with these holders, we can apply the electricity, light, heat, and gas and liquid flow onto the sample and directly observe the reaction dynamics at a nanometer or even the atomic scale. So our TEM lab has been equipped with many of these cutting-edge in situ holders, including the heating and the electric holder, the liquid nitrogen cooling holder, and also the liquid and the gas holder. So next, I will use our recent work to demonstrate the power of the in situ liquid holder. So for this holder, the sample will be loaded on this silicon nitride membrane, and the liquid flow can be conducted within these two membranes so that it will not affect the vacuum of the TEM column. And the liquid thickness is limited to be less than 5 microns so that the electron beam can penetrating through to image the dynamic process. And this membrane is also coated with electrodes, which can perform liquid heating and the electron chemistry. But due to the presence of the liquid, the atomic resolution imaging will not be achieved. So we can only perform the in situ observation with nanometer spatial resolution, which is still the highest resolution among all the in situ techniques. So this is one example in which we are looking at the manganese oxide catalyst. So here we conduct the solution of the chemical oxidant, the CIN solution. So soon after we conduct the solution, we can see the development of nanobubbles around this catalyst. So these are the images extracted from this movie. And so here we can clearly see the growth of this nanobubble around the catalysts. As these bubbles can only develop around the catalysts in presence of the chemical oxidant, so they must be the oxygen bubbles from the oxygen evolution reaction. So to our best knowledge, that is the first direct observation of the OER process at the nanoscale. So with this great progress, still the resolution of this observation is too poor to see what may happen on the catalysts. So in the next observation, so this is the reaction mechanism, how the CIN solution can initiate this chemical OER process on this manganese oxide. So in the next observation, we managed to achieve thinner liquid thickness so that we can have a higher resolution to see what happens on the catalysts. So here, after we conducting the CIN solution, still we can see the development of the nanobubbles as indicated by this blue arrow. And more excitingly, we can see the simultaneous formation of the surface layer on these catalysts. So maybe you can look at this process again. So here the nanobubble is really small, so I hope you can see this weak contrast. And this red arrow indicates a nucleation site for the surface layer, which eventually propagates to cover the whole catalyst surface. So this surface layer formation indicates that some surface restructuring process during the OER. And as the surface layer is less than 4 nanometers thick, so to clearly resolve its formation dynamics, it means our spatial resolution should be less than 1 nanometer. But still, we cannot achieve the atomic resolution under this condition. So these are the images extracted from that in situ movie. With the sub-nanometer resolution, we can still measure the variation, the time variation of the oxygen nanobubble size and the thickness of the surface layer as indicated by these blue and the red curves, respectively. So we can see that for this oxygen nanobubble, it does not grow continuously, but shows this oscillation behavior. So this means that the competition between the oxygen evolution and the dissolution. During this observation, we are conducting a constant liquid flow, so we can consider the dissolution rate is constant. Therefore, if the OER rate is higher than the dissolution rate, the oxygen bubble must grow, otherwise the oxygen bubble must shrink. So the volume changing rate should reflect the local OER reaction rate. And for the surface layer thickness, it also shows this thickness oscillation, which means the formed surface phase is highly reactive. So it can either dissolve into the solution or reacted recover back to the manganese oxide phase. So, but as the time goes on, this surface layer thickness still increase to be between 3 and 4 nanometer. which indicates it's a partially reversible surface restructuring process. And with these two curves, we can further calculate the Pearson correlation coefficient, which is about 0.41. So this positive correlation indicates that when there are more surface layer, the oxygen bubbles will most likely to grow. So this indicates the surface layer should be active in the OER catalysis. So the next question is, what is exactly this active phase? So with the poor resolution during the in situ liquid TEM observation, we cannot perform a detailed characterization on the surface layer. Fortunately, this is a partially reversible process, which means after we take the sample out of the solution, there will be some residual surface layer for us to do the ex situ characterization. So here we performed the identical location ex situ TEM. So the catalyst originally has a clean surface. After conducting OER for a few minutes, we can clearly see a surface layer developed, which appears to be amorphous. And then we performed the spectroscopic mapping, which shows that the surface layer has a different fine structure compared to the inner region. The surface manganese shows a reduced valence compared to the manganese 3 inside the lattice. And for the oxygen spectrum, this first peak corresponds to the hybridization between the oxygen 2p and the manganese 3d orbitals. So the reduced oxygen peak at the surface indicates the less oxygen coordination around the surface manganese atom, which basically indicates the presence of the oxygen vacancy. So overall, we conclude that this surface layer should be manganese oxide in the amorphous structure and with reduced manganese valence and the oxygen vacancies. So besides the liquid TEM, the other very popular in situ holder is this scanning probe holder, which consists of these two probes that can be moved relative to each other. So if we coat one probe with the active material, such as cobalt oxide, and the other probe with the lithium, which will be oxidized to the lithium oxide, which can act as a solid electrolyte. And when these two probes get in contact with each other, it forms a nano battery, which can perform charge-discharge cycling inside the TEM. So this way, we can directly observe the lithiation-delithiation behavior on this active material, as demonstrated here. So this is a cobalt oxide nanopillar. And upon the lithiation, we can clearly see the volume expansion together with the formation of the nanocrystalline phase, which is probably cobalt. And upon the delithiation, the nanopillar will shrink. And this expansion and the shrink will continue upon more cycling. So we can quantitatively measure this volume change as shown in this blue curve. We can see the volume expansion can be as large as 200%, which is quite big. So this big volume expansion eventually leads to the failure of this material, which explains its instability during the cycling. And if we change the morphology of this material to the nanosheet, we can see the similar lithiation process, but now the volume expansion will be greatly reduced. That is attributed to the large surface area of this nanosheet to accommodate the lithium. So this nano battery setup not only applies for the lithium, but also works for the sodium and the potassium. Here we collaborate with our colleague, Dr. Zhang Biao, and we compare the intercollection behavior for the lithium, sodium, and potassium on the MOS2 crystal. So the reason we do this comparison is because the electron chemical measurement shows that for these three types of battery using the MOS2, the potassium battery shows the best stability, which is counterintuitive, because we usually think the stability is limited by the volume expansion, and the potassium battery should give the largest volume expansion for MOS2. So it's quite a surprise. The potassium battery gives the highest stability. So to solve this puzzle, we performed the in situ observation. It shows that at the early stage of this intercalation process, indeed, we can see the expansion of the MOS2 layers. And so the increase of the layer spacing will increase from the lithium to the sodium to the potassium. So the potassium indeed shows the largest lattice expansion compared to the pristine phase. However, as the intercalation process goes on, the molybdenum sulfide layered structure will be destroyed for the lithium and the sodium case. So that indicates that when the lithium and the sodium accumulates inside the MOS2, the intercalation process will be switched to a conversion process so that the layered structure of MOS2 will be decomposed and destroyed. But for the potassium case, the intercalation process still continues and dominates, so which help to preserve the layered structure of MOS2. So this this tendency for the conversion reaction for the lithium and the sodium has been confirmed using the DFT calculation, which explains the better stability for the potassium ion battery on the MOS2. So the next example is one of our most recent work. Here we use this nano battery, try to explain the performance of this co-share electrode material. So by preparing this nickel oxide coated with cobalt oxide, the cycling stability can be greatly improved compared to the pure nickel oxide. So to understand this stability improvement, we performed this in situ the lithiation, delithiation cycling. It shows that for the pure nickel oxide, its volume expansion is quite big, which eventually leads to the failure of this nanoparticle. And this will cause the loss of active material and also the capacity. But for this co-share structure, the volume expansion appears to be limited, so that this whole particle will remain integrated upon the whole lithiation process.
Dr. G, 5 minutes left.
Okay, thank you.
We need to leave some for the question time.
I see. Okay, so I will be quick then. So then we need to understand this different volume expansion behavior. So to do that, we first probe the lithiation mechanism for this material. And we prepared this special coin cell, which includes this TM grid loaded with active material. Then we measure this voltage profile for the discharge charge cycling. And this voltage plateaus indicates the intermediate reactions. So we just stop at this voltage and take the TM grids out for the ex situ TM observation. So I will skip the detailed characterization results. So basically, it shows that at this 1.2 volts, the lithium will first accumulate at the surface and reduce the copper oxide to copper 2O, and the lithium will be oxidized to the lithium oxide. And if we further lower the voltage, then all the oxides will be reduced to the metallic phase. And if we go to the opposite voltage, lithium can be retracted from this co-share structure and leave a lithium-rich SEI layer and also the nanocrystalline cobalt and nickel oxide. So after we understand this two-step lithiation process, we can then understand the volume expansion. So due to the presence of the copper, which shows a less volume expansion, indeed, this co-share structure should give a smaller volume expansion compared to the nickel oxide. But this difference is not very big. So to fully explain the different volume expansion behavior, we also need to measure the kinetics. So from the in situ TM, we measure the volume expansion rate. The nickel oxide indeed show a much higher volume expansion rate compared to this co-share structure. And the co-share structure shows this two-stage volume expansion corresponding to the two-step lithiation process. And we have also theoretically confirmed this lithiation kinetics using the chemomechanical simulation. So at last, I briefly show this cryo holder, which can help to preserve the vulnerable SEI layer on the electrode. So this is quite a useful technique to look at the beam-sensitive materials on the active electrode material. So this is my summary slide. I show how this sub-angstrom imaging and atomic scale spectroscopic mapping, as well as in situ TEM, can help to contribute to the energy material research. And at last, I would like to advertise for our new TEM, which is close to the end of the installation process. It is featured with ultra high resolution, about 0.5 angstrom, and also equipped with the low dose ultra fast camera, which is very good for the in situ observation, and also got the cryo capability for the beam sensitive materials. So we welcome all the interesting collaborations. So thank you very much for your attention.
Thank you, Dr. G, and thank you very much for giving us a very interesting talk about your research here. I would like to know, is there any question from the audience? Feel free to ask question. You can open your microphone, ask question, or you type your question in the chat box if you feel comfortable. Maybe I start with a question first. Yeah, Dr. Ju, you in the first few slides you saw us the capability of the TM. They can actually distinguish between different size or different mass, atom with different size or different mass. So I would like to know, yeah, what sort of a difference you can dissolve? For example, if I look at the periodical table, yeah, for example, the element carbon, nitrogen, and oxygen, they're close to each other, right? So for element like this, can they actually be distinguished with the current technology?
So if you want to distinguish it from the electron scattering, that will be difficult for the carbon, nitrogen, and the oxygen because they are next to each other.
Yep.
So that's sort of the smallest difference, right? But we can always try to distinguish them using the spectroscopy, such as the EELS. So if we can do the EELS mapping at the atomic scale, we can still be able to distinguish carbon and oxygen. They have very different characteristic peaks. So that's a way to do it.
The spectroscopy instead, right?
Okay. Yeah, spectroscopic mapping.
So is it the material looking at is a single layer material? Or...
Oh no, this is a bulk material. It's just we are looking at the cross section. In cross section, this is
cross section of the bulk material.
Yeah.
So it don't need to be very thin, right?
No, well, it cannot be too thick. It's better to be less than 50 nanometer, but 50 still, nanometer. Yeah, it's reasonable thickness.
So they can only focusing on specific layer, right?
Yeah.
Okay. So you actually demonstrate that you generate some kind of gas bubble within the TEM. Is it? Mm-hmm. So basically, for this, you're generating oxygen or hydrogen, or what sort of gas you're producing in that chamber?
It's oxygen.
It's oxygen, right?
Yes.
So is it this performance is very uniform or regular? Because I have a feeling that for bubble generation or gas generation, there's many factors that might influence the process. Indeed.
So you can say for all this in situ observation, you definitely need luck because it's a complicated system. And say if you do not see any phenomena, you don't know what's wrong. So what we can do is just spend a lot of time and efforts to continuously doing this observation until we get the result.
I guess, right, with the same process, the same material, and if you do it 2 times or 3 times, you might have some variation between them, right?
True. Yes, but this variation is understandable considering the whole process is very complicated because when you load the material, it's never at the same location, and see this chemical solution may have different, slightly different, impurity, and well, yeah, let's say so this process, if we can manage to observe it multiple times, we already consider it to be repeatable, but we do not expect to observe it every time.
I see.
Because there can be problems that we do not fully understand.
Yeah, it's very challenging, right? Yeah.
Yes.
Very nice. Very nice work.
May I ask a question?
Yeah, sure.
Hi, thank you, Peter. Thank you very much, Dr. Zhu. Very interesting topic and very fascinating technique. I'm wondering, because you want to do a lot of in situ technique, right? In situ TEM. How in situ can it be? For example, the pressure, the temperature, especially when you talk about OER, HER, maybe photocatalytic, thermocatalytic. What is the limit currently, and how to improve it?
Okay, that's a good question. So even though we are claiming to do the in situ observation, the environment may not be completely the same as the microscopic measurements, the reaction environment. So in terms of OER, so for example, the liquid thickness is limited to be 5 micrometer. If it's thicker than that, we will see nothing.
5 micrometer.
Yeah, we do find that with the thin liquid layer, the behavior of the this reaction will be different, probably due to the flow rate or the local concentration of the solution will be different. So we were told that the thicker the liquid, the more it will resemble the microscopic measurements. But in order to go to the nanoscale, we have to go to the thin liquid layer. So we have the limitation like that. So we cannot, at least for the OER, yeah, it's not exactly the microscopic environment yet.
How about the pressure?
The pressure, we can only control the pressure using the flow rate.
Okay.
Yeah, so we do not have a direct control over the pressure. I actually never thought of this question. So the pressure, because it's a liquid reaction, the pressure on the OER rate is an important factor.
No, just talking about some other like thermal catalysis reaction.
Okay.
Yeah, because I'm working on something similar as well, operando technique, in situ technique.
Yeah,
okay. Interesting to discuss with you maybe later.
Okay.
Yeah,
because for the gas holder, the pressure will be important. So we have the control for the gas reactions, but for the liquid we don't.
Okay.
Yeah.
Thank you very much.
Mm-hmm.
Okay. If no more question, then we can move to the next section. Let me introduce.
That will be me.